Okay, so let's go ahead and jump in and get this show on the road. Let's see, where are we here?
What chapters is the quiz going to cover?
It'll cover chapter 3 a little bit, and then most of what we've been covering up to now. So basically, mostly chapter 4. I would say 80% chapter 4, 20% chapter 3. After you go through chapter 4, you almost automatically review chapter 3. So. Okay, and let's see, where are we here? Okay, as a review from last week, I'm going to go over Rutherford's scattering experiment. His purpose when he did this experiment was to show that, excuse me, Thompson's plum pudding model was valid. Thompson's plum pudding model, all the alpha particles should have been shooting right through with no obstruction. Now, if you remember from his experiment, he took a source of alpha particles, which are very heavy particles. It's 2 protons and 2 neutrons, and he used that as a ray gun to shoot through some gold foil. What happened was, instead of everything going like this down here, where everything shot through, he was getting some of this, and also deflections. So this should have been 100% straight shot through, verifying Thompson's model. And remember, in science, we always verify other scientists' work. If you can't verify their work is not valid. That's called peer review. And you'll hear that a lot currently now in all the COVID stuff with the vaccines. And it's important to understand that the only tests that are valid are peer review tests. Peer review means that scientists in your field, your peers, are reviewing this and saying, oh, this is valid, it makes perfect sense. If your peers say this is all BS, then your paper that you're presenting will not be published. So peer-reviewed studies are extremely reliable results. Okay, hence, that's what Rutherford was trying to do with this Thompson model. Thompson said it's a plum pudding model. We've got electrons and protons equally. Excuse me again. My gosh. Oh, I've got a big glass of water here. It doesn't seem to be helping. Thompson's model said if we shoot through the plum pudding model, everything will go through unimpeded, just right on through. What happened was we got this bouncing. Stuff was happening inside there. There was something that was very, very hard and dense inside the atom that was bouncing these particles. So Rutherford's experiment was credited with creating the concept of the nucleus. The nuclear model, that means that most of the mass, like 99.99% of the mass of the atom, is located in a very, very tiny spot in the atom. And that spot is called the nucleus, and it's made up of protons and neutrons. Now you can see the approximate size of an atom, 10 to the minus 10th meters. The size of the nucleus is 10 to the minus 14th. That means it's 10,000 times smaller. It's extremely small. Hence, this area here basically is nothing with electrons running around in there. And as I said before, this was a big deal because it's basically the atom is made up of nothing except for this little dot of mass. Very, very strange idea. Even to this day, if you were to go outside and stop someone on the street and ask them, does this sound weird that most of matter is nothing except for these little dots of extremely dense mass surrounded by these flicking little electrons that weigh hardly anything? Would they believe that? No, they wouldn't. So that's what Rutherford was facing with his colleagues. Now, along came a guy named Bohr, and Bohr wanted to put some organization to these electrons. Now, Rutherford had no electron organization whatsoever. They were just kind of running around that empty space. Bohr said, no, that's makes no sense. I have experiments to show that there's more organization to these electrons than just randomness. Okay, so one of the principal parts of Bohr, there's a number of parts to the Bohr model of the atom. One is, think of the planetary model. This is classic. You always see this model of the atom on the right here, where you've got a nucleus in red and you've got all this stuff running around it. Okay, really, if we're looking at hydrogen with one electron, this is what Bohr's model looks like here. However, the concept of the orbit is an area for electrons to be stable in. Okay, so the orbit is an area for electrons to be stable in. That's why they stay there. They don't wander outside that area because it's not stable. So they find these areas of stability, which happens to, now this is again Bohr's model, which is, I'm going to talk in a minute about Bohr's model has some issues. But anyway, for right now, Bohr's model said that we have these orbits, which are areas of stability for electrons, and they are nicely going around the nucleus. Kind of the concept of a solar system, planetary system. Okay, and additionally, there are other areas of stability running around that nucleus. We also call those orbits. They don't have any electrons in them though, but there are areas of stability. And they're well defined by Bohr's model. And you don't, and the areas outside those orbitals are very unstable. So the electrons are either going to be in the orbitals or not. In the orbitals or not. Okay. So an orbit, stable area for electron to reside. Some are more stable than others. And that stability has to do with potential energy. The more stable orbitals have lower energy. Outer orbitals have higher energy. So the electrons want to reside in an area of the most stability, which is closest to the nucleus. So if we look at this model again, notice that the electron is residing in the orbital, the stability area, closest to the nucleus, not out here, but inside, really close to the nucleus. Now, it makes sense. The nucleus is positive, the electrons are negative, opposites attract, so that's going to be the most stable from that perspective. But there are other areas that are also stable outside that inner orbital. But not as stable as the inner ones. Because the area outside the orbital is so unstable, Electrons are only allowed in certain orbitals, or they're quantized into those orbitals. In other words, it's in or out, nothing in between. Black and white, in or out. Now, an electron can go from one orbital to the other. Because the potential energy or the energy is different from one orbital to the next, energy is either released or absorbed, if that should happen. And that's the part that Bohr observed, is that we have this, we can move electrons from one orbit to the other by either adding energy to the system or pulling energy out of the system. Now, if you took hydrogen and excited it big time with a couple thousand, probably 30, 40,000 volts, you're going to start exciting those electrons in the inner orbitals, and they're going to start jumping to those other orbitals because they have excess energy. And what happens is that's not as stable as the inner orbital. So what happens is the electrons want to return to that stable orbit. When they do that, they give off energy. It takes energy for them to go to the outer orbitals, which are unstable, but when they return, they give off energy. And that energy is a specific frequency, a specific frequency. And it looks like this when you look at it through a prism. So these are specific energies of the electrons jumping from one orbital to the other once they're excited. Nothing in between. Nothing in between. Because those areas outside the orbitals are so horrendously unstable, they don't go there because it costs them too much energy. So they stay in the orbits. This is what led Bohr to come up with this concept. Okay, so the experiment is this. You excite electrons in gaseous hydrogen, and it ends up having these certain energies given off, in this case, visible light, and only 4 of them for hydrogen. Now, it depends on the element that give off more or less because they have more electrons, but hydrogen's the simplest, it's just 1 electron. And it has to do with this bouncing around. So, so what we're doing is we're putting energy into the system. Boom, electron here goes there. Electron here goes there. It's unstable. So what happens? They want to become more stable, so they return here. When they return, they give off a specific frequency. And the frequency is invisible light, so it appears like a line. And this is called a line spectrum. And you can use that diagnostically. Okay, so you go to the doctor and you run a talk screen. What they do is they go through and they know that certain chemicals will give off a certain line spectrum, and they can then identify from the line spectrum of that chemical what it is. It's like a fingerprint. But what makes the line spectrum are these electrons jumping around to various orbitals. So you put energy in the system, they jump to a more unstable orbital, they don't like it there, so they come back down. When they come back down, they give off energy. And in the case of visible, now some of them are ultraviolet, some of them are infrared, but when they're visible, in the visible spectrum, you can see them. So we have, this is what neon looks like, helium, hydrogen. Notice hydrogen is simpler because it only has one electron. Helium is more complex because it has two electrons, and so on. The more electrons, the more complex the line spectrum is. This is another reiteration of that. Okay, so the light is a result of electrons transitioning from one orbit to another. And when I say light, that is infrared, visible, and UV. All those are examples of energy being given off. The visible we can see. The infrared we cannot see. The ultraviolet we can't see unless you're a bumblebee. Okay, and again, this is kind of saying the same thing. All right. So we have the Bohr model, and Bohr did pretty well. He got a Nobel Prize over this. Concepts. His concept worked really well for hydrogen, but started to fall apart remarkably for anything but hydrogen. There was a lot of very fancy high-end math when you take your quantum mechanics, your physical chemistry class. You're going to get into quantum mechanics. You're actually going to show all these calculations, and they are massive, but it works pretty well for hydrogen. Breaks down for anything else. So this guy named Schrodinger said, well, maybe there's something more to this than just orbitals. And through some very fast, not fast, but fancy math, he said the orbital idea doesn't work from a mathematical basis on a lot of theory on physics, atomic physics. And he said, really, we're talking about a statistical probability of finding an electron in a given location. We're not sure how it got there. Bohr's model said, oh, it's just like a planet revolving around the nucleus. No, not like that at all. Schrodinger said, I can go to a certain area and I can calculate the probability of finding an electron there. I don't know how it got there though, but there's a high probability of finding one there, which could be stretched analogously to what an orbital is. Okay, this is our current model. Not the Bohr model. The math and the chemistry fit the quantum mechanical model better than the Bohr model. And we distinguish these statistical areas by calling them orbitals versus orbits. So an orbit is a cylindrical, more like elliptical area of high stability around the nucleus. An orbital is an area around the nucleus where there's a high statistical probability of finding an electron. Okay. All right. Now, to further understand chemical reactions and reactivity, we need to understand more about what electrons are doing what, because the chemistry the non-nuclear chemistry is determined by electrons around the nucleus, not inside the nucleus, but around the nucleus. So the more you understand about the electrons around the nucleus, the better you understand the chemistry of that element. So that's what we're going to talk about now, is we have to understand how these electrons are organized around the nucleus. Okay, so if you look at the periodic table, there are 4 areas that reside statistically. In other words, high probability of finding them. Okay, and we've divided those up into S, P, D, and F areas. Okay, S, P, D, F. And if we understand where the electrons are located, we can then figure out what the chemistry should be based on those electrons, where they are. And again, remember, we're using the quantum mechanical model now. There are areas around the nucleus where statistically there's a higher probability of finding an electron than other areas. Higher probability, of course, means more stability, and that's where the electrons like to reside. Okay, the periodic table is organized based on these areas. And this is the way they're broken down. Elements that fall into this area are called S block elements. And that means that the electrons in their outermost shell are considered S electrons. And they have a particular shape. These elements have P electrons, and they have a particular shape that's different from the S. D's are different, F's are different. So there are 4 groupings where these electrons are statistically arranged for stability reasons, okay? And we call those orbitals. Okay, now, if you notice this periodic table, there's all these little guys here. Okay. Those identify the electrons in that particular element and where they're located from a statistical perspective. Okay. Now, let's look at hydrogen. Hydrogen is located right here. Okay. How many electrons does hydrogen have? It has 1. That 1 electron is considered an S electron, and it's at level 1. That's the closest to the nucleus. 2 is further out, 3 is further out, all the way to 7. So 7 is the furthest out, least stable. 1 is the most stable. So if you're going to have 1 electron, where do you want it to be? You want it to be closest to the nucleus, not out here, because that's not as stable. You want it to be closest to the nucleus. And remember, we're not using Bohr, we're using the quantum mechanical model. So if I was to ask you what What are the electrons in hydrogen? You'd say there's one electron. It's in the innermost area, region 1. I'm going to give that a name. It's called a shell. So it's in shell 1. And it's in the S block. Now the S blocks have a particular pattern to them. Let's see, down here, I have that for you. I don't have it. Tomorrow, I'm going to show you what these look like. Sorry, somehow that got erased. The P's have a shape. The D's have a shape. The F have a shape. Okay, so going back to hydrogen. Hydrogen has one electron. It's at the first shell, first level, the closest to the nucleus. And it's in the shape of an S block. Okay. S block are, think of it spherical, uniformly around the nucleus. That means the probability of finding that electron is anywhere 360 degrees around the nucleus. Let's look at helium. Okay, so hydrogen has one electron. Helium has 2 electrons. Also in S, also at the first level. So that means helium's 2 electrons are located also around the nucleus at the same level of those electrons from hydrogen, only helium has 2 electrons. So we have 2 of them buzzing around in a uniform spherical shape around the nucleus. Lithium has 3 electrons. However, lithium's 3 electrons are not all located close to the nucleus because we filled up that area. So what happens is, what's the next most stable area? That's level 2. And those are also S electrons that are evenly distributed around. So this gets complicated. You know, when you look at uranium has 92 electrons. Well, it's a whole bunch of, you know, where are they located? Really complicated. So what we've done is we've done a way of numerically designating what electrons are where, in what orbital. And that's done with these here. So this says shell 1, subshell S, we have 1 electron in the subshell S, and the whole thing is on shell number 1. Shell number 1 means it's the closest to the nucleus. Let's look at lithium. These are all lowercase, by the way. Okay, so this is on shell 2. subshell S, we have one electron in it. Okay, so it's shell 2. Subshell S, and one electron in the subshell S. Okay. So basically what we're accounting for, we need to count, excuse me, we have to account for all the electrons. Because, as I said before, by accounting for all the electrons in what, my goodness, by accounting for all the electrons in what orbitals are in, we can predict the chemistry of that element. So if notice the difference between hydrogen and lithium isn't so much the subshell or the number of electrons in the subshell, it's the shell that's different. That's what determines the chemistry, is what's in the subshell, not so much the shell. So if the subshell is the same, then the chemistry is going to be very similar, if not the same. I mentioned groups all have the same chemistry. It's because their subshells are the same. In the case of the alkali earth metals, beryllium, magnesium, calcium, strontium all have S2 as a subshell. 2 electrons in the subshell S. Hence their chemistry is the same. Now you guys have all been really quiet. You have any questions so far? This is kind of really different stuff.
And more so, I feel like I need to just practice more on this.
Yeah, there's a lot of practice in the worksheet. And this will not be on the quiz, too, by the way. Okay. Let's see. My notes have been cut off. Where is my notes? Wow, this is weird. Right here, there's about 4 pages of notes that aren't there. I'm not sure what happened to them. When we look at electrons, let's look at lithium's electrons. Lithium has 3 electrons. Now, this symbol here represents the outermost electron. The outermost electron, singular now, the outermost electron is located at shell 2, subshell S, and we only have 1 in there. But how many electrons does lithium has? It has 3 electrons. What about the other 2? Okay, so that's the nucleus of lithium. We have 2 electrons, and then we have one electron. The one electron is 2s1. We also have two other electrons. And that's located in these locations. Okay? So those other two electrons are closer to the nucleus. But because we ran out of space in that close orbital, we overflowed into the next one out, okay, which is the 2 level. So these inner electrons are called core electrons. These outer electrons are called valence electrons. So usually, not all the time, but most of the time, 99% of the time, we have two kinds of electrons. We have core electrons and valence electrons. Because these inner electrons are extremely stable, because they're extremely stable, they do not participate in the element's chemistry. Only the outer electrons participate. In the element's chemistry. So frequently we don't look at the core electrons because they're so incredibly stable. We look at only the outer valence electrons because they determine the chemistry. And that is what is displayed on this periodic table. These are only the valence electrons. Beryllium. 4 electrons total. 2 are core, 2 are valence. Right there. 2 are core, 2 are valence. And the core you can ignore because they're extremely stable. They won't do anything because they're so stable. The valence electrons are not all that stable. And that's why that determines chemistry. Because what do they want to do? They want to become more stable. They become more stable by combining with other elements so that the other elements' valence electrons can commingle with beryllium's valence electrons. And hence, the compound will become more stable. Okay, and this is how it's arranged. Notice something weird here. You know, this. So we have 7 shells. Within each shell, there could be, well, okay, and here we have subshells are going to be the S, P, D, F. Okay. In some of the shells, we only have 1 subshell. In other shells, we have S and P's, or S, D, P's, or S, F, D, P's, subshells. And then each subshell can support differing numbers of electrons. Depends on how many orbitals are within the subshells. Okay, so we have shells, subshells, orbitals, and then electrons associated with the orbital. So these have 3 parts: shell, subshell, orbitals. Okay. Now, we've covered a lot of very, very, very cryptic stuff today. I'm sure you've never heard of this before. The reason why we're covering this is because from this, we can predict why copper has a +1 ion, or why copper has a +2 ion, based on its electronic configuration, based on how these electrons are in various orbitals and subshells. It also shows why groups, the alkali metals, the alkali earth metals, the halogens, the noble gases, have a particular chemical behavior also. So this whole idea of assigning electrons to certain shells and subshells and orbitals really is important, because it shows us and predicts the chemistry of that element. Okay, so what I'd like to do is end this lecture by going through and configuring some elements. And then tomorrow I want to pick up on that big time and really get into this, because this is a little on the cryptic side, but I'm going to show you some little ways to make this less cryptic. Okay, so we're going to do some simple ones today. Let's look at beryllium right here. Okay, a couple things. Beryllium has 4 electrons. Beryllium is in shell 2. It's located in the S block. And there are 2 electrons of the 4 that are in the S block. Now, that is 2 of the 4. What about the other 2? Okay, these are the valence. The other 2 core. Those reside up here, on the top here. So to get to beryllium, we're going to go 1, 2, 3, 4. Now, we're going to go 1, 2, and that is not on shell 2. That's on shell 1. Until we get the shell that the element is on, those are all core electrons. So we have 2 electrons in the core, and those are S. So that's going to be in shell 1, there are S electrons, and there are 2 of them. So the total configuration for beryllium is 1s2, 2s2. Core. Valence. And remember, the core don't matter because they're so stable. They don't do anything. Only valence. Only valence electrons do anything. Only valence electrons. I can't emphasize that enough. So the valence electrons totally determines the chemistry of that element. So beryllium has the chemistry of 2s2. Because that's the configuration of the valence electrons. All right, so let's now grab hold of magnesium. Magnesium has 12 electrons, I believe. Yes. Okay. And where is magnesium located? Okay, it's down on the 3rd shell. And it has 2 electrons in the S block. Okay, so that accounts for 2 of the 12 electrons. There are 10 more electrons. Those are all core. And what is the configuration for those core electrons? Well, we start here and kind of we have shell 1 electrons, shell 2 electrons. Shell 1 electron, we have 2 there. And in shell 2, we have 8 electrons. How did I get 8? Well, 1, 2, 3, 4, 5, 6, 7, 8. 6 P's, 2 S's, plus 2 S's from here. So this is where the 10 electrons are. So now we have electrons accounted for. We know exactly where the core electrons are located. We know exactly where the valence electrons are located. Valence. So if you look at the total configuration, electron configuration for magnesium is going to be valence. So beryllium has got a valence of 2s2. Magnesium has a valence of 3s2. S2, S2. That means the chemistry of the valence electrons between magnesium and beryllium are the same, hence their chemistry is the same. The core electrons do not matter. They matter in terms of mass, but not chemistry. They matter in terms of physical characteristics, mass, not chemical characteristics. Okay, so I'm going to end that here, and we're going to pick up tomorrow and do a zillion of these. A zillion of these. I'm going to talk a lot about this core. There's a way to abbreviate the core. I'll show you a little shortcut so you don't have to write these out. And remember, think about uranium, 92 electrons. And we have to count for all 92 electrons when we write an electronic configuration, just like we accounted for 12 electrons here with magnesium, 4 electrons for beryllium. If we do uranium, we're going to account for 92 electrons. And there's also some anomalies regarding this here. That's kind of weird. And also these guys. That we'll get into in depth tomorrow. Okay. Very intricate stuff. Now, remember, excuse me, the quiz will not cover chapter 9. Only 3, mostly 4. And it'll be available sometime tomorrow, hopefully tonight, but for sure sometime tomorrow. And it'll be due Saturday midnight. Now, you're going to be limited on time. This is going to be a real proctorial quiz where you're limited, and it's not going to be take home like the exam 1 was. Remember, only exams 1 and 5 are take home. 2, 3, 4 are going to be like tomorrow's quiz. Okay, wasn't that fun? This is the most cryptic of the class. This, along with chapter 5, is a little mathy cryptic, but this is a non-math cryptic. So this is as cryptic as it gets. And well, tomorrow will be more cryptic, but basically chapter 9 is the one that's killer. Okay. Wasn't that fun? All my students, I've been doing this since 1974. All my students go, oh my gosh, are you kidding me? So it just takes lots of practice. And I'm going to go through lots of examples, lots and lots of examples. And I'll be doing some on Monday as well. I'll be doing lots of examples. I want to make sure you're comfortable with this idea of electronic configuration. Because when you get into 400, they're going to hit this heavy duty again. And if you understand this well in my class, you'll do fine in 400. Okay.